Okay, let's get started. Today is our great pleasure to have Dr. Jiequn Han to give us a talk in this seminar. So let me say a few words about Dr. Han. Dr. Han is now an instructor at the Department of Mathematics, Princeton University. He also obtained his PhD degree in Princeton as well. His research draws inspiration from various disciplines of science and is devoted to solving high-dimension problems arising from scientific computing. His current research topics mainly focus on machine learning-based multi-scale modeling and solving high-dimension partial differential equation and stochastic control problems. So, Jiequn, I give you all the control, please. Thanks.
Okay. Thanks for the introduction and thanks for the invitation. And it's my pleasure to give a talk on the curse of memory in recurrent neural networks, especially the approximation and optimization analysis. So this talk is based on our paper under the same title, recently accepted by ICAOR 2021. So this work is mainly about analyzing the relationship between learning and dynamic systems when we use recurrent neural networks (RNN) as a tool to learning temporal relationships. So this is a joint work with Wei Nan in Princeton, Qianxiao Li in NUS, and Zhong Li in PQ University. So let me start with the background. So as I said, when we use recurrent neural networks to learning temporal relationships, it involves learning problems and dynamic systems. So if we stand at a higher level, it involves interaction between machine learning and dynamic systems. So in this sense, we can put three categories of their interactions. So the first category is study dynamic systems via study machine learning via dynamic systems. So in this sense, I mean, we can, for example, we can take a control perspective to look at the deep learning as a composition of multiple functions. We can use numerical analysis tools based on dynamic systems to study the effect of dynamic systems. So this line of research has drawn a lot of research interest in recent years. And the second and the third type of interactions are more like inverse side, using machine learning to study dynamic systems. And here, the second type and the third type has slight difference. The second type I call the machine learning of dynamic systems. So that means we have underlying truly dynamic systems. Okay, we know our data is generated by certain dynamic systems. So our goal is to learn the dynamic systems from the observed data or observed trajectories. So this is like a system identification problems. If we know the form of the dynamic systems, we want to, for example, we want to use machine learning tools to determine certain coefficients or unknown parameters of the dynamic systems. Or we want to use the similar idea to do model reduction to generate a machine learning model to describe certain important variables or variables or degree of freedom generated by dynamic systems. And the third type is called the machine learning for dynamic systems. So this is a bit different from the second thing in the sense of that we are given an input sequence and output sequence, and we want to use the machine learning to construct a dynamic systems to model their relationship. So in this sense, it's not necessarily true that the underlying data is generated by a true dynamic systems. Instead of that, we want to construct an approximating dynamic systems that characterize the structure presented by data. So applications of this kind of goal is like, for example, the simple case is like time series forecasting or time series classification, or in a lot of machine learning tasks, you want to do sequence-to-sequence models, or in the context of dynamic systems, you want to learn a partially observed dynamic systems. So you know the four dynamic systems is complete, but if you want to construct a paradigm dynamic systems, you have to come up with a new dynamic systems. So today's talk will be in the third type. Especially, we want to use machine learning tools to construct a dynamic systems that explain the sequence or temporal data structure. Okay, so why would we interested in this kind of thing? So we will still work in the supervised learning context. So the supervised static supervised learning is formulated in this way. Okay, we are given some input data X. For example, in the image classification, it is image, and our output Y can be some category variable, so it's a classification, or it can be a real numbers, so it becomes a regression problems. So our target is to learn a function f star such that yi can equals f star xi. So we want to map the image of cat to the category variable cat, and we want to map the image of dog to the correct category as well. So in this sense, if we want to do static supervised learning, we are learning a static function f star using information from the data set consisting of a lot of data pairs xi and yi. Okay, so this is the classical setting up, and in a lot of real applications, it is not that is not enough, because our input data and or output data may be formulated as a dynamical sequence. So this is very common in a lot of applications, like the price forecasting. Given the past prices, we want to predict tomorrow's prices. Or in the machine learning, in the machine translation tasks, given the context, a sequence of words, we want to translate into another language. Or again, using dynamical systems as example. For example, if we consider a forced dynamic systems, so we want to learn the temporal response given a temporal forcing input. So in all these kind of applications, essentially we want to learn a sequence to sequence mapping. So there are several common features in these kind of problems. So each output essentially depends on the sequence of inputs. The inputs actually becomes a sequence, and given this kind of input feature, we need to model a sequence of input-output relationships, because you can imagine, okay, the mapping determines the today's price given the history is a mapping, and the mapping determining tomorrow's price given the past price will be a new mapping. So in this sense, we are not determining a single mapping, but instead a sequence of mapping indexed by the time variables. So this is the key structure that makes us interested. Given a temporal or sequential structures, we would like to learn a sequence of input and output relationships, and this aspect naturally requires us to investigate the interaction between dynamic systems and the learning problems. Okay, so if we put it into rigorous mathematical language, in a static setting, we are given a vector x, the input vector in d-dimensional space, and an output vector y in the n-dimensional space. We want to learn a target function f star. And in the dynamical setting, we are given a sequence x indexed by the variable k. K can be either discrete time index or continuous time index, and our output can also be an index indexed by k as well. And our target is to learn a function hk star, which also depends on time index k. So if we change the k, in this sense we are learning a family of functionals depending on time variable k. Okay, so if we still stand in the context of supervised learning, we want to learn or approximate a sequence of functionals hk star. And So one way or typical way people have known for a long time to do this kind of task is to use recurrent neural networks. If you are not familiar with this, so here is a simple introduction for the RN architecture. So given a sequence of input xk from x0, x1 to xk minus 1, we would like to construct a hidden state hk from h1, h2 to hk. So each hidden state, so the hidden state hk follows this kind of dynamic systems. So we apply a linear transformation w on the previous step of hidden state, and apply another linear transformation of the input signal with matrix U, and then we apply certain nonlinear activation element-wise activation sigma. So you can interpret this, the total effect of this. The first line is like a single layer a neural network. Of course, we should also specify some initial conditions of the hidden state. So by convention, it is specified as 0, or in some specific attacks, you can specify the initial conditions as you like. And then we model the output y as another linear transformation based on the hidden state hk. So this give us the recurrent neural network in the simplest case, given based on one layer hidden state and one layer output layer. Of course, you can following the spirit of deep learning, you can construct more operations for the dynamics of hidden state and more operations for the output layer, but this is the main idea of recurrent neural network. And you can see, given this kind of architecture, essentially the recurrent neural network gave us a parameterization of a sequence of functionals, because once given the parameters capital W, capital U, and the vector small c, we determine a family of functionals hk hat, which gave us a mapping from x0 to xk minus 1 to yk. And if we change the time index k, this mapping is always well defined, given the parameters w, u, and small c. Okay. So in this sense, training recurrent neural networks is essentially adjusting parameters c, w, u such that our parameterized functionals hk hat is close to the ground truth hk star as close as possible. Okay. So as I mentioned, from the outset, the recurrent neural network approach parameterize a sequence of high-dimensional functions together. So this functions is high dimension because you can see the input dimension depends on the time variable k. So as you increase the time t, the essential dimension becomes larger and larger. So to make sure our recurrent neural network can do a good job in terms of representation or parameterization, you can imagine the sequence of functions that can be approximate in this way must contain certain structure. Okay, it is hopeless to expect that our recurrent neural network can approximate arbitrary functionals. Okay, so in this sense, this viewpoint is similar to a reverse side of the Morris-Wansink formalisms developed in the non-equilibrium statistical mechanics. So in the Morris-Wansink formalisms, we want to construct given a partially observed Markovian dynamical systems, we want to use it to describe a fully observed systems with memories. And the RN essentially wants to do something in a reverse side. We observed certain systems with memory, and we want to construct a partially observed systems with hidden variables hk. So in this sense, with augmentation of hk, the systems becomes Markovian, and we want to use this partially observed Markovian systems to explain the original observed fully observed systems. Okay, so this is a brief introduction of recurrent neural networks. So if we study these learning problems, so we have several questions we can ask. So we can roughly put them into 3 categories. So we usually call it 3 paradigms of supervised learning. So the first thing is that we have a target functional H. We have a target functional H star, and we use recurrent neural networks to specify a hypothesis space H hat. So the first thing we can ask is that, okay, the best model for, in our hypothesis space, given a best model in our hypothesis space, what's the distance between our target functional and our best model that is realizable by our hypothesis space? So this is called approximation error. And the second thing is that, okay, if we want to find the best model in our space, we will rely on some optimization procedure. So the typical choice is some gradient or stochastic gradient based optimization methods. We start with some initial guess of the parameters, and with optimization or training algorithms, we end up with some learned model. Okay, and then our learned model may not be the best model because we only have because we in the real optimization we will only use finite data samples, and this finite data samples is a Monte Carlo approximation or Monte Carlo sampling of the Monte Carlo sampling of the true sampling. So here you can see our learned model, and the distance between our learned model and the best model can be characterized by two difference. The first thing is called optimization error. So that is defined as the distance between our learned model and our model defined by the empirical risk minimizers. So because it's possible due to the non-convexity of optimization problems, we do not find the exact minimizer of the empirical risk minimization problems. And the second thing is distance between our minimizer based on the empirical risk minimization and the total expectation, the expected risk minimization. So this distance is called the generalization error. So you can see the approximation error, generalization error, and optimization error, 3 types of errors together characterize our difference between the target functionals and our approximation models. And in this work, when we analyzing the recurrent neural networks, we will mainly focus on the first part, the approximation error and optimization error. So that will be the focus in today's talk. Okay, so what's our main questions we would like to ask? So we would like to look for a precise analysis of what's new when we do supervised learning in this dynamical setting, in contrast to the static setting. So to make this analysis concrete, we first need to formulate these problems in a rigorous mathematical language. So we would like to introduce the following simplification. So first, we would drop the nonlinear activation. Instead of that, we will consider a linear activation. Okay, so hk plus 1 equals whk plus uxk. Second, we would like to take a continuous time limit for the original dynamic systems. Instead of discrete time dynamical systems, we consider its continuous time analog ht dot equals wht plus uxt. Okay, so these are 2 starting simplifications that we introduced for this setting. Okay, so these 2 simplifications seems too simple, but you will see later on that the dynamical features of our supervised learning problems are preserved under these 2 simplifications, and the key properties of influencing the learning problems, such as the regularity and the memories, can be precisely formulated in our continuous time formulation. So use the mathematical language, we can specify this kind of the concepts, the regularity or memory easily, and make it rigorous. And furthermore, based on with the help of the linear activation, we can perform a quite complete analysis that highlights the key issues when we consider the approximation problems and optimization problems. Okay, so when we talk about continuous time formulation, let's again specify the input space and output space. So here, input space is a compacted functions from mapping from time variable into a d-dimensional sequence, to a d-dimensional variables. So each element in this input sequence, each element in this input space actually is a path in the d-dimensional space. And because it is a Banach space, we can introduce this the super norm for this space. And the outer space, and without loss of generality, we assume the output space is one-dimensional. So it is a bounded sequence from a bounded mapping from time variable to a scalar value. Okay. Again, this Y is a sequence, is a path in the one-dimensional space. Okay, and now our target functionals, the true functionals is denoted by H star t indexed by t, and yt is given by ht star x, and x is the whole path of the input. Okay, so in this setting, our recurrent neural networks especially specify our hyperspace in the following sense: ht star equals wht plus ux, so ht dot equals wht plus uxt, and yt hat, the output, equals c transpose times ht. So here ht is an m-dimensional hidden state, and w is called the recurrent kernel, given the relation between on the hidden variable, and capital U is the input kernel, and the C is the output layer weights. So you can see M, the dimension or the size of the hidden state, is some number we can choose a priori. So if we have a larger M, usually you can imagine we have the larger hyperspace that can better approximate the underlying target functional, and of course we will have larger computational cost. So in this sense, we can specify our linear RN hyperspace in the following sense. So let's focus on this part first. So this ht hat x is given by this formula explicitly, because given the linear RN relationship, it's just a linear ODE, we can write down the solutions explicitly. It is just a convolution or integral over the signal from -infinity to up to time t. And here we will encounter matrix exponential determined by the recurrent kernel W. And to make it stable, because we will study the functionals as t goes to infinity, so we want to make sure the functional is stable. So we additionally require the eigenvalues of W must have negative real parts, such that this functional is well defined for arbitrary large time t. So this h hat gives us the linear RN hyperspace when we after we decide the size of hidden state M. So this h hat is the union of all the possible M's. Okay. So is any questions for the setting of the linear RN space? Yeah, please feel free to interrupt me if you have any questions. Okay, now given the formulation, the questions we can ask specifically in terms of approximation and optimization is the following. Okay, what sequence of functions can be well approximated by those functions in the hyperspace H hat? Okay, this is about approximation, and how does the optimization dynamics behave once we choose to optimize in this linear RN hyperspace space. Okay, so let's start from the first part, the approximation theory. Okay, the key problems we can ask in approximation aspect is, first, what class of functions can be well approximated by H star to by H hat to arbitrary precision? So this is like a universal approximation theorem we have seen a lot in the case of neural networks or kernel functions, because this is the first step questions. The next step, okay, we can further ask what's the approximation rate, or in other words, what classes of functionals can be approximated efficiently by H hat, okay, meaning that we can use a reasonable small size m to approximate the functions accurately. So we will answer both questions in our work. Okay, so one important remark I want to make is that in our formulation, we do not assume that the target functionals ht star are generated by some underlying dynamical systems. Okay, in other words, there need not exist a dynamic systems where the ht star x equals yt, where yt is given by dynamic systems. Yt is the functions determined by ht, and ht star is given by a dynamic systems of f ht xt. Because in this case, our neural networks, our recurrent neural networks is more will be more like learning functions g and f. And once we can approximate g and f in our recurrent neural networks, we can of course approximate the whole functionals very well. So this is a common setting in a lot of prior works. And in here, we do not assume these quite strong assumptions. We are only given a temporal input and output pair, which is not necessarily generated by a dynamic systems. Okay, but although we do not assume this kind of structure, but we should expect that the functionals can be well approximated by our linear RN should have some structure. Okay, so here is the first thing is a proposition of the hyperspace H hat. So so if our H hat T a family of functionals in our linear RN hyperspace space, then we can easily prove that the H hat star is continuous, a linear functional. Okay, this is determined by our linear RN structure, and H hat star is a causal functional. Okay, which is also intuitive because our output yt does not depend on the future input xt to xt or xt plus 1. It only depends on the past input x0 to xt minus 1. So in this sense, ht is a causal functional. And the third one is just a mathematical property. It is also a regular functional because the regular means that if our input signal converges to zero input in certain sense, then our output signal will also give us zero output. So in that sense, you can imagine our output signal. Our output signal does not depend on infinitesimal segment of the input signal. And the last property is also very evident. The family H hat T is time homogeneous because our coefficients C, W, and the capital U are time independent. So the functionals determined by these parameters is also time homogeneous. So these are just straightforward properties of our linear RN. And our a side remark is that the last three properties also hold true for nonlinear activations. So, okay, then here comes our first result of the approximation theorems. So, so actually, this kind of properties, given these properties, as long as our target functional ht star is also a family of continuous, linear, causal, and continuous linear, causal, regular, and time homogeneous functionals on X, then within arbitrary position epsilon, we can find a linear Rn functional in our hyperspace H hat, such that the supreme norm between H star and H hat can be is no larger than epsilon. Okay, so this is a reverse side of our properties of linear functions. So you can interpret it as a universal function, function approximation theorem in the Rn setting. Okay, so I will not go through the main the proof of the theorem, but the main idea is to use the general Riesz representation to express the linear functional H star X by certain density rule. Okay, because this is the basic result in linear function analysis relating the functional to certain density, and then our recurrent neural network approximation problems is reduced to the L1 approximation of the rho t by the kernel C transpose times e to the power of Wt times u. So it's essentially like an exponential sum approximation problems. So if you are interested, you can look at our paper for more details. Okay, so this is our first result, but it does not give us an explicit function approximation rate. So you can imagine, although all these kind of functionals can be well approximated by our hyperspace, but it's not tell us how large n we should choose. In other words, we will expect that not all functionals can be equally approximated. So our next goal is to investigate which functionals are easy to approximate and which are not. So this is a more interesting problems of our practice interest. Okay, so the key concepts in answering these questions is the so-called smoothness and the memory properties. So suppose we have an input functional looks like this xt. Okay, so and the first functional ht star gave us an output yk looks like this. So we can see this time the output seems very smooth. So this is something nice, and we can another feature in this mapping is that you can see our t becomes 0 after the middle time step. Okay, it becomes 0 something, and you can see this phenomena is immediately represented in the output signal, because our output signal gets saturated after time past the middle time step. So in a sense, you can see the yk seems to have a very short memory. It responds to the input signal very instantaneously. So in contrast, the right-hand side functional seems much more challenged, because you can see first the output signal is quite rough. So the regularity or the smoothness is quite bad. And secondly, even the input signal becomes saturated after in the second half of time step. The output still varies a lot. So that means it depends on the long memory. It depends on the long memory of the input signal. It even depends on the beginning of the input signal. So we would expect that the left type of functional is easy to approximate, and the right type of functional is difficult to approximate. So how do we make this kind of intuition precise? So to this end, we introduce a standard basis vector, EI, in the d-dimensional space, and we would construct a bold-face EI as a constant signal when t is non-negative. So then we can introduce the concept of smoothness and memory based on the output signals respect to our constant signal EI. So we define the output of constant signal as YIT. Then the smoothness is characterized by the smoothness of the functions YIT, and the memory is characterized by the decay rate of of the YIT or certain derivatives to the case order the case derivative of the YIT. Okay, so in other words, by looking into the output of functionals or the output of constitutional signals, we can investigate the smoothness and the memory of our family of functionals HT star. Okay, now here comes our second main result of approximation rate.
May I ask a question, Jiequn?
Sure.
So you have the assumption sort of the smoothness of the mapping, but do you have the assumption of the smoothness of the X in terms of T? So you always assume that's a smooth, or you have like a
we do not assume any smooth of the input sequence, the input signal X.
Or even X may have like a huge jump, then you still that space, the hypothesis space is still good enough to capture such a thing?
Yes.
But
because you can think even H is not regular enough, but after a convolution of a nice density rho under the Rees representation, then we still have a nice output signal Y, and that is enough for us to talk about the approximation.
Okay, thanks.
Yeah, that's a very important viewpoint. Thanks for asking that. Okay, so now we give an explicit approximation rate in terms of the smoothness and the memory. So here smoothness is specified very straightforwardly. We just assume YIT has alpha plus 1 derivative, alpha plus 1's odd derivative, and in terms of memory, we assume that up to alpha plus 1 order derivative, YIKT would have exponential decay with a velocity e to the power of minus beta t. So in other words, e beta t times yi to kt goes to 0 as t goes to infinity. And of course, given this thing, we can also specify a uniform constant gamma in the following sense. Okay, then given this constant, we can prove that there exists a universal constant C alpha that only depends on alpha, such that for each given hidden state size m, there exists a functional in the linear space of size m, such that the supernorm of H hat and H star is bounded by the following expression: C alpha times gamma times d over beta times m to the power of alpha. So apparently, you can see as we have larger m, we can have a better approximation. So this is not surprising. And let me add some more remarks on this result. Okay, so this is our rate estimate. The first thing is that, okay, the smoothness dependence alpha is what we would expect in approximation theory. So this, for example, in Fourier analysis or harmonic analysis, we have already seen, okay, the smoothness will determine our approximation rate in the following instance. So we have the similar result in our dynamical setting. This is not surprising. And what is new is the dependence of beta and gamma, especially on the beta. Okay, gamma is just a constant given the beta, and you can see the assumptions means that our temporal derivatives of the signal yi, the output signal yit, must decay like e to the power of minus beta t for certain positive number beta, and then our final function rate, our final approximation rate is also determined by beta and gamma. If we have larger beta, that means we have larger decay, or in other words, the memory effect is small, then we have better approximation rate. So qualitatively, it matches our expectation. Okay, and the third comment is that you can see here there's no curse of dimensionality. Okay, the d is just a linear factor comes into the final approximation rate. This is not surprising because we are working in a linear setting, so the dimensions can be separated in a linear fashion. So this is normal. But the one thing hidden in this result is the so-called the curse of memory. Okay, so what do I mean by the curse of memory? I mean if our output signal YIT do not satisfy exponential decay e to the power of minus beta t, but only have algebraic decay, something t to the power of minus omega, where omega is a positive number, then as omega goes to 0, we can see in order to get an error epsilon, we need to require our size m in the order of omega times epsilon to the order of 1 to the power of 1 minus 1 over omega. So you can see this kind of exponential dependence is very similar to the so-called curse of dimensionality in the traditional setting. So here the factor is the memory is here the factor is the memory factor, the memory variable omega. So if we have a long-term memory, meaning that omega is very close to 0, then our requirement on the size m would be exponentially large. Okay, so this is just an implication of our approximation rate. So let me explain this point in more details. So you can see as you can see, our previous result will require our function output YIT has an exponential decay. So what happens if our functional has long-term memory? So in other words, it does not have exponential decay. Okay. So in the simplest case, let's construct an example like this. So this is determined. This is again formulated in the Rees formulation. We have HT star given by specified by the integral of the input signal with a density rho s. Here rho s is in the order of t to the power of minus 1 plus omega. So the whole thing is still integrable, but as omega approaches 0, it becomes the memory becomes larger and larger. Okay, so in this sense, our output signal has the order of t to the power of minus omega. So it has non-exponential decay. So how do we obtain an approximation rate to this kind of function? Okay, so one way to consider approximation is to introduce a cutoff time capital T, which is if sufficiently large, then we just approximate the density rho s up to time capital T. Okay, then our cutoff will give us an error estimate as order t to the power of minus omega. Okay, then for the approximation between 0 to capital T, we can apply our previously obtained result is c to times gamma to the power over beta times m, and gamma is obtained by this way. Okay, this is our definition. So with some optimization by choosing, because we are introducing a cutoff, of course, it is exponential decay for arbitrary beta, as long as time is large enough. So we can optimize over different beta. And after some simplification, we can finally get an error estimate in such a form: c times t to the power of minus omega plus omega over m to the power of t times t to the power of 1 over omega. So to make sure we achieve an error of order epsilon, we would require t to the power of minus omega have the same order. Then to work out the second order term, we can immediately derive that our m should be in the order as I claimed previously, omega times epsilon to the exponential order. So this is what I mean by the curse of memory. So once we have a long memory functionals, then we would need exponentially large hidden state to approximate the original functional accurately. Okay, so to summarize the first part, we formulate the problems as an approximation of linear functionals by linear recurrent neural networks. And our first result states that there exists a universal approximation theorem for the linear functions. Okay, so basically it can approximate all the possible space, all the functionals have the same properties as the linear recurrent neural networks. And our second result is more interesting. It gives us an approximation rate which relates to the smoothness and the memory to our approximation rate. And from this rich result, we can get a key insight, the so-called curse of memory approximation. So you can see this memory of approximation is not about the usually talked the explosion and the vanishing of the gradients. So the explosion of and the vanishing of gradients is about optimization problems. And here we only stand at the perspective of approximation. At the level of approximation, we have already encountered a serious issue if our target functionals have very long-term memory, and we can make this long-term memory dependence very precise in the case of linear functionals and the linear recurrent neural networks. So this problems is about the recurrent neural network architecture itself. It's not about optimization problems. So that's our main findings in the approximation part. Okay. Is there any questions? I can pause here to take questions regarding the approximation. Okay. If there's no questions, I will go into the next part, the approximation, the optimization aspect. And interestingly, you will see the curse of memory again arise in a very similar picture. Okay, it also affects the difficulty of the optimization dynamics very evidently. Okay, so let's first formulate our optimization problems clearly. Okay, so we would in the simplest case we would consider the risk minimization problems. We want to minimize the difference between our predict output and the true output. And suppose we are only interested in the final time output, capital T, and the imprecautions, and we should also consider the distribution of our input space X. So our loss function looks like this. And because we have a explicit formula for the linear functionals, so we can write the loss function in this way. And of course, if one considers the sequence-to-sequence model, then we also need to take another integral from over the time, because for small time t from 0 to capital T. But to make things easier, we will stick to the first line only to the on the sequence to scalar model. Okay, and we will consider the gradient descent dynamics. Okay, and update the parameters small c, capital W, and capital U in the following sense with certain learning rate eta. Okay, and then to motivate our analysis, let's look at some numerical example first. So you can see so the first picture and the second picture is about learning linear functionals. Okay, so we specify our true target functional by certain density rho. So in the first picture, the rho is just a nice decay functions determined by a certain exponential sum. So it's very smooth and decay fast enough. And you can see if we apply gradient descent, the loss function decays very nicely. And the second term, in the second example, if we specify our density rho t as an array function, okay, it is an integral function. It is oscillatory at the beginning and finally gets saturated, converging, going to 0 at larger time. Okay, interestingly, you can see given this kind of true functionals, our learning becomes much more difficult. We will have a certain plateau phenomena in the middle of the learning dynamics, and finally get out of the plateau phenomena and continue decreasing the function values. Okay, so the first two examples are the linear functionals. If we consider a nonlinear dynamic systems using nonlinear recurrent tools. So this is what people do in practice. Suppose here the example is using nonlinear recurrent neural networks to learn the forced Lorentz dynamic systems. So essentially, the mapping between the input force and the output trajectory. And if you use the recurrent neural networks, you can see we will also encounter certain plateau phenomena in the middle. Okay, so our question is, okay, what is the source of the plateaus during the training? Okay, so apparently for certain functionals there's no plateau, and for certain functionals there's plateau phenomena happening. Okay, and our answer will again related to the memory factor introduced in the first part, the approximation part. Okay, so to make our analysis amenable, we need to furthermore introduce certain simplification. Okay, so we will take X to be the standard winner process, so we can apply the isometry to get rid of the expectation of X. So it becomes L2 difference between the two kernels. And then we assume the D is only one-dimensional, so this is not important. And for simplicity, we assume T goes to infinity, so this will make the integral explicit. And finally, we will assume that our W, in order to compute the gradient easily, we assume we are restrict the recurrent kernel in a diagonal case. So in other words, W is diagonal, so then we can combine the vector small b and small c into another vector A. So our hyperspace becomes an exponential sum. So it's essentially we would like to find optimal parameters AI and WI with size m, such that the exponential sum can approximate the true target density rho t accurately. Okay, so this is the loss function we would like to analyze under the GD dynamics. Okay, so although this is this requires some further simplification, but once we accept this as simplification, we can get a very intuitive insight to see why the plateau will happen. Okay, so let's look at the gradient under this kind of loss functions. Okay, respect to AK and WK. Okay, these two gradients are very similar. So let's look at the second line. Okay, only. So the gradient is an integral over two terms. Okay, so the first term is exponential term. Okay, t times e to the power minus wkt. Wk is also of course positive, and the second term is the residual term. Okay, the residual between our exponential sum and the two terms, and our targets. Okay, so when will plateau happen? So the plateau happens only when the gradient of j is small, but the function itself is not small. This is where we would encounter the plateau phenomenon. Okay, so this kind of thing will happen when the residual is large only when t is large. So when t is large, then the exponential term is small. So if the residual term is only large when the exponential term is small, then their product is still very small. The total integral is very small. So the gradient is very small. But since the residual is large when t is large, so that their L2 norm of the original loss function can still be very large. So in this sense, we would encounter the plateau phenomenon. So in other words, the large error part is compensated by the exponential term when we're calculating the gradient. Okay, so you can see when will this kind of thing happen? This is again related to the memory, because if we have very long-term memory, then it is very possible we have already approximated the short memory part well, but have certain difference between on the long memory part. Okay, so let's consider a special case. Okay, suppose we will use the risk representation, and suppose our true target rho t is in the following form. Okay, rho bar is a nice function, like in the expansion sum, and the rho 0 WT is the memory term. So we assume it's a compacted functions, and the memory effect is characterized by the factor omega. So you can see here rho 0 omega t is obtained by shifting the temperature function rho 0 by with some distance 1 over omega. So as omega approaches 0, the target memory increase larger and larger because we have a bump or spike at a very long time point. Okay. So if we apply the gradient descent learning on this kind of spatial density, we can clearly see the insight we introduced at the beginning. Okay, so you can see as 1 over omega increase from 10 to 15. Okay, you can see we'll encounter larger and larger plateau phenomena. Okay, so you notice that here the time unit increase, and when we encounter the large time when we encounter the plateau phenomena for loss function, you can see the gradient is as expected very small. Okay, so you can see. Okay, so this is our numerical finding, and theoretically, how can we make it precise? So our result is based on the following program. Okay, so first we specify certain symmetry of our parameters because our two parameters, our short memory part is an exponential sum. This is our short memory part, and of course there are certain permutation symmetry of the parameters a hat and w hat, because up to permutation and combinations they are equivalent. And then we can show that at this kind of well approximated short memory part, the function values of Jm is bounded away from 0, while the gradient of the gradient is quite small. So that explains the plateau phenomena. And furthermore, by calculating the Hessian, the eigenvalues of the Hessian matrix, we can estimate, okay, how long does it take for the optimization dynamics to escape this kind of plateau region by performing a local linearization analysis to obtain the plateau time scale. So this is the overall idea for the optimization for the analysis of the optimization dynamics. And our main result is as follows. Okay, suppose we start with some parameters that approximates the short memory part. Okay, then our dynamic systems will get stuck in the plateau with a time scale e to the power of c over omega square, and log 1 over omega. So you can see here, omega is the memory factor, and as omega approaches 0, we have the factor e to the power of 1 over omega. So this is again the curse of memory. And in the analysis of optimization, we reveal another facet of the curse of memory in the optimization dynamics. Okay, and so numerically, of course, we can verify that our the log of our plateau time scale is proportionally to c over omega when omega is very small. And although we do our analysis in a simplified case, but you can see if we abandon the diagonal assumption, if even in the four matrix case, the optimization will still encounter this kind of plateau phenomena. So that implies that the plateau phenomena due to the long-term memory is a quite generic phenomena for this kind of temporal sequence learning. Okay. So I will wrap up my results quickly. So in summary, in this optimization part, we analyze the gradient flow of linear recurrent neural networks, and in the setting of rho consisting of rho bar and a long memory part, we can analyze precisely the dynamics near rho approximates to rho bar, and we can observe the plateauing phenomena, and we can derive that the plateau time is at the order of c to the power of c over omega. So this will give us the curse of memory. This is, of course, more precise than the vanishing gradient or the explosion gradient, and that reveals the dynamical integration, the interaction between the recurrent neural structure and the target function. Okay, so the summary of the whole work is that you can see, although we analyze the recurrent neural network in a simplified setting, but our result is quite non-trivial. The overarching theme is that we can see the curse of memory plays a very important role in both approximation and optimization. Okay, so that gave us a specific characterization what kind of functionals is easy to approximate and optimize, and which functionals are not. Okay, so of course we would like to extend this kind of thing to nonlinear case and to other recurrent neural networks. To other temporal structure models like LSTM, transformers. So right now there are a lot of debates over transformer is better than LSTM or vice versa. We hope that in our simplified setting, the linear setting and the continuous setting, it is already enough for us to gain some insights over different choice of architectures. And our final goal is to come up with a theory of interactions of dynamical structures in models and data. So the model itself is not enough to make the whole story complete, because as you can see, the temporal structure carried by the data itself, like the memory effect, is very important in determining our final learning performance. Okay, so I think that's the end of my talk, and I'm happy to take questions.
Thanks, Jiequn, for this very nice talk. Any questions so far? Question? I do have a couple questions. Maybe, let me ask one. Because of time, then maybe we can talk offline a little bit if you're
sure.
free. So my main question is, so in your proof or assumption, you have sort of assumption about the continuity of the HT. So you sort of control the smoothness of H depends on T. But in practice, well, you haven't really talked about the sampling X, right? In practice, what you have is really like a XT and YT. You sort of have some kind of control or jump. That's actually the question I asked before. Right? You have some continuity or jump of the training data XT and YT. So based on that, can you sort of learn something in terms of H that you have the control behavior of H instead of you assume H has such a nice behavior?
Can you repeat your question again?
So my question is that, so if I don't know, so I just to give you training is like I have a bunch of XT, I have a YT. So they may have some continuity or smoothness behavior in terms of T, but I don't know the property of the HT. Based on such a thing, can you predict or can you still have the nice approximation behavior without assuming you know the continuity of the H?
Yeah, I think that would be quite challenging in our current framework, because we're assuming HT is regular. So that was what I mean is that certain small if in the continuous time setting certain small change of X over an infinitesimal on the input X will not bring large difference of the output of Y. So if that is not the case, then it will become our the functional space much larger, because it's possible that that means that if we change one input variable as a time sequence, then the output can be geometrically different. Then right now we do not have a good idea to talk about approximation in this sense. Right? So you can. So if the HT is not continuous, then that means even you have the same path history, but if your last time step input is slightly different, then your output becomes quite different. So this kind of thing. So this kind of functional HT is much more irregular, and so far we have not have good idea to deal with the approximation for
That
this
makes
kind of
sense. That makes sense. Okay,
Mhm.
I see. Because of time, so I don't want to hold the rest of the audience for a while. So maybe let's stop here. Thanks, Jiequn, again for this very interesting talk.
Yeah,
So
thanks for the
I'm
invitation.
gonna stop the recording. So